In this part of the video, we are going to continue to cover examples 3 to 6 in lesson 57. So hopefully you got a chance to try some of the questions on your own because you're learning actively by doing that first. Okay, so here we go. Solve 5 times 2 to the power of x plus 3 equals to 10 to the power of 3x. We cannot multiply the 5 and the 2 together and fake the base of the power on the left side. So we're going to make use of some properties of log or natural log. If I log both sides of this equation, ln of 5 times 2 to the power of x plus 3 equals to ln of 10 to the power of 3x. This will allow me to separate the multiplication on the left side here into ln 5 plus ln of 2 to the power of x plus 3. And then on the right side, I can immediately write 3x in front of ln x. We can do the same to the second term on the left side and get x plus 3 times ln of 2. After this step, I'm going to expand x plus 3 times ln 2 and also gather like terms. I'm going to put all the x's on the right and all the numbers on the left. Okay, so here I have ln 5 plus, now because this is x ln 2, I will subtract that from both sides of the equation and then continue with expanding 3 times ln 2. This way, I can actually factor out x on the right side of this equation. I get x times 3 ln 10 or ln of 10 to the power of 3 minus ln 2. And then on the left side, I will actually try to combine the two terms together. So I can multiply 5 by 2 to the power of 3. Okay, let me take one more step first. So 8 times 5 is 40. If I think about the right side here, this is really 1,000 divided by 2 when I write this as a single ln. So this is ln of 500. As a result, x is equal to ln of 40 over ln of 500 as required above to put the answer in ln A over ln B. Okay. Number 3b. So I have two powers of different bases, so we can't compare the exponents right away. So again, I'm going to start by taking the natural log of both sides of the equation. So I have ln of 3 to the power of 2x equals ln of 5 to the power of x minus 1. Again, using the power of log, I can bring the exponent to the front. Expanding on the right side, it's going to give me two terms. Again, I'm going to gather like terms on the left. So 2x ln 3. When I expand the right side, I get x ln 5. So now I'm going to do subtract x ln 5. This is equal to negative ln 5. That's okay. We'll keep it in this form first. On the left side, this will help me by factoring out x. I'm going to have ln of 3 squared, which is 9, minus ln 5. This is negative ln 5. Then I have x equal, or x times, let's take one more step, ln of 9 over 5. Okay, and then negative ln 5. So now you can use your calculator and divide negative ln 5 by ln 9 over 5. And x is equal to negative 2.74 rounded to 3 sig figs. How did you do? Okay, take a look at example 4. We have a system of equations involving x and y. So let's solve this system of equation. Well, when I look at first equation, I can rewrite it into exponential form, which probably will make it easier for me to substitute that into the second equation. And perhaps I can also write the second equation into exponential form. So let's see. So here we go. X cubed is equal to y. Let's call this equation 1. And then here we have y plus 1 to the power of 1/2 is equal to x plus 1. That's equation 2. Okay, that's not too bad. So because we have y isolated in equation 1, let's sub 1 into 2. And so what do we have here? We have y is x cubed. So x cubed plus 1 to the power of 1/2, I'm going to write it as a square root, is equal to x plus 1. It seems that I have to square both sides now. So x cubed plus 1 is x squared plus 2x plus 1. Now we have x cubed as a polynomial equation. Let's bring everything to the left and make right side equals to 1. Minus x squared minus 2x plus 1 minus 1 is 0. So, okay, so we can actually factor out an x. So x times x squared minus x minus 2. Looks like we can keep factoring. X minus 2, x plus 1. Okay, so we'll just pretend that we're solving this polynomial equation for now. We know that x will be 0, or x will be 2, positive, or x is negative 1. However, in our context, we're really dealing with logs. So don't forget, when we're looking at logs, we need to make sure the variables that you get, or the solutions that you get, there are no extraneous roots whatsoever. Well, x serves as a base in equation 1. So that means I cannot accept this value. When x is equal to 2, that's fine in both equations. And when x is equal to negative 1, well, negative 1 plus 1 in equation 2 gives you 0. Log of 0 doesn't exist. So this is also extraneous. So we're really just working with x equals to 2. So let's continue to find the value of y then. So for x is equal to 2, equation 1 shows us that y must be equal to 8. So let's do a quick check again. In equation 1, the original form, can I have log base 2 of 8 equals to 3? Yep, checks out. And how about check in equation 2? I have log of 8 plus 1, so 9, of 2 plus 1, 3. Is that equal to a half? Yes, checks out. So that's good. So therefore, the solutions must be x equals to 2 and y equals to 8. So let's move on to example 5 and 6 on the next page. You're asked to find exactly the points of intersection of two equations. Well, since y is isolated in both equations, that's convenient. I'm just going to number here, equation 1 and 2. And we're going to set 1 equals to 2. We get x to the power of x minus 3 equals 1 minus 3x, e to the power of negative x. So I got negative x and x. That's not nice at all. Well, what can we do? What can we do? What can we do? Well, let's bring everything to the same side first, I guess. Minus 3 minus 1 is minus 4. Okay. Still ugly, right? When you run out of ideas, start going crazy. Why don't we factor out e to the power of negative x, the lowest exponent of e? Then, what does it look like? E to the x divided by e to the negative x gives us e to the power of 2x. Plus 3 minus 4. Well, we have to divide the original term by a common factor. Turns out you will get this, which is a quadratic equation that involves e to the x. All right. So you have a coefficient of 1 for the square term, so to speak. The sum is negative 4. The product is 3. Okay. So when we factor this, what do you think? We will have a 3 and a 1. We need negative 4 as a sum. So that must be negative for both factors. As a result, you theoretically have e to the power of negative x equals to 0, or e to the power of x equals to 3, or e to the power of x is equal to 1. X is ln 3, no problem. Or x is ln 0, or ln 1, which is 0. How about here? Ln 0 doesn't exist, right? So there's no solution in this part, and therefore you get these two results. Last but not least, let's take a look at an application question. So the question says, the population A of t in thousands of a city is modeled by the function A of t equals to 80 times e to the power of 0.02 t, where t is the number of years after 2020. A, by what percentage is the population increasing each year? And B, in what year will the population reach 1 million? Well, the most direct way to find the percentage without any shortcuts, that's what I mean, is by comparing, well, your population in 1 year to the next, and then look at the percent increase, right? So for simplicity, we can definitely use easy numbers. Let's compare the population between year 1 and 0. And then the base here must be the population in year 0, and we multiply this by 100%. So what does this give us? We have 80 times e to the power of 0.02 times 0.02 times 1, so it's just that, minus 80 times e to the power of 0, so it's just 80 over 80 over 100%. We know all the 80s will be gone. So technically, you're really dealing with e to the power of 0.02 minus 1, and then multiplied by 100%. This gives you, 2.02%. Is this a coincidence that you have an exponent for e that is 0.02, so roughly 2%? Go figure. Okay, part B. In what year will the population reach 1 million? Now notice how you have to make sure you read the questions very carefully, because A of t is actually recorded in thousands. So when we are talking about 1 million, this is 10 to the power of 3, or 1,000. Okay? So all we have to do is to substitute 10 to the power of 3, or 1,000, as A of t in this case. So we want to end up with this population in the formula. To solve for t, I know that I'm going to take the ln of 10 cubed over 80. Right, I simplify that first and then ln both sides, so that I have 0.02t ln e. And this works out to about 126 years. Now the question asks for in what year. So don't answer the question, say after 126 years. That's not good enough. You should put this back into context, and knowing that year 0 is 2020. So we're really looking at the population will reach 1 million in the year 2020 plus 126, so 2146, so 2146.